Welcome, everybody. For those that don't know me, my name is David Berry, and I'm a member of the Industry Committee of the WCIT. I know that there are some people registered and as guests here this evening who are not members of the worshipful company of information technologists. You're most welcome, but I should just explain that the WCIT is then the 100th livery company in the City of London. And as you might gather from its name, it combines centuries-old tradition with a modern focus and an innovative approach. But like all livery companies, we look to give something back to the industry and our community, and are founded on 4 pillars of activity. The 4th pillar is industry. And this evening is a slight departure from the usual industry committee seminars, when we've looked at how IT is creating new opportunities and transforming other industry sectors. So for example, we've looked at smart buildings, smart cities, shipping, flight navigation, motor vehicles, insurance, etc. But it's long been my long belief that there's a great story to be told about the role that IT has and will have in our understanding of the impact of human activity on our world climate, and IT also to help tackle the climate change crisis. It's been said by somebody called David, not me, someone a bit more famous than me, that we're the first generation to fully understand the climate change crisis, and we're the last generation able to do anything about it. It's for this reason that the WCIT has established a climate change working group headed by Martin Hawley. So Martin, I think over to you just to say a few words about that working group.
Thank you, David, and good evening to everyone. Yes, it's a very new working group, so we started it last year, and we've got 3 main aims in the group. First and foremost, it's about informing ourselves and others in the IT community about what climate change is about, and broadly, it's just a lot of questions really we have. It's what can be done about it, and the timeframes that things are possible in. I think we're also really understanding the reality of what is needed. For example, is offsetting a viable practice? When do we have to do things by? We talk about net zero 2050, but actually, also this decade is called the decade of delivery. So a lot has got to happen in the next 10 years. And then, really importantly, exploring how information technology can be used as an amplifier for mitigating climate change. So we want to see who's doing what in climate technology, and maybe how can we help. So that's the sort of informing ourselves side of it. Then there's a sort of we want to ignite interest in others. So we want to bring more people into our sphere to learn with us and also to contribute to our own learning. So we may start some sort of chain reaction really, and understanding and influencing. And that's the 3rd aim really, is that we do want to influence. And we think we'll do that organically, but we're doing things like we're starting an impact group of IT leaders to enable them just to get together and share ideas and the initiatives they're doing, the actions they're taking, so that we can help influence, create direction and some momentum throughout the IT industry. So they're the broad aims of what we're doing, and we're growing a working group. We started off with about 8 or 9 people. We've now got about 15. So the group's growing, and I really invite anyone to get in touch if they're interested in that and interested in joining. But for the moment, back to David.
Martin, thanks very much. So whilst I had the idea for this seminar, I've really done very little beyond speaking to Jim and Amanda. And to be frank, Amanda Carpenter and Jim Hayward of Account Management have pulled this seminar together, arranged all the speakers on the panel. So rather than wait to the end, I'm going to thank Jim and Amanda now in advance for really pulling everything together and organizing this event, and handing over to them now to facilitate the proceedings from here. So over to Jim and Amanda. Thank you.
David, thank you very much, and Martin, thank you as well. It's great to be thanked before we've delivered, so that's actually quite nice. I think perhaps the pressure is maybe on, it's even more. But yeah, it's fantastic to have the opportunity. We're really grateful to have been asked to facilitate this discussion, and certainly something we've been looking forward to for a while. I'm going to show you some slides in a second, but maybe just a very quick word about Accio Management. We are a small consultancy, and we bring our experience of organizational development and environmental consultancy to help the various clients that we work with and make sure that they're helping to make their businesses more sustainable, more productive and more profitable, and obviously doing all that without costing the earth. So if anybody thinks there's something that we could support you with, we'd be delighted to have a conversation. What I'll do is let me just start by sharing my screen. So you've seen me, so you can now see some of the slides, if I may. So delighted to be joined tonight by three fantastic guest speakers. We've got Ian, Helen and Michael, and I'll introduce them in a second, but each of them are going to give some insights and some thoughts into their own particular area of expertise where IT is already playing a significant part to save the planet. And after they've spoken, we're going to open things up for a discussion, which Amanda's very kindly going to facilitate. So what I'd suggest is that obviously if you've got any burning questions, please do perhaps put them in the chat or raise your hand or something, but certainly we'll have a fulsome Q&A after our three guest speakers have spoken. Excuse me, I'll just change this slide properly. So Dr. Helen Brindley, reader in Earth Observation at the Faculty of Natural Sciences in Imperial College London's Department of Physics, and she's the co-leader of the Earth Observation Network, and her areas of research focus on the measurement and interpretation of the Earth's outgoing radiation to space and how this is linked to climate variability and change. And Helen's currently working closely with the European Space Agency to develop new satellite missions to monitor and understand Earth's changing climate. So again, hugely relevant. And then Professor Michael Mainelli, among many other things, is the executive chairman of ZEN Group. And Michael describes himself as a scientist financier trying to promote societal advance through better finance and technology. And that hardly seems a long enough introduction to cover such a deep and wide background, one which also, I should add, includes Alderman and Sheriff of the City of London for 2019-2021. And then Dr. Ian Campbell is the CEO and one of the co-founding team at Breathe Battery Technologies, or Breathe. Ian has produced battery modeling codes used around the world today, and he co-founded Breathe in 2018, prior to which he consulted widely on electrification and battery technologies. And what's particularly interesting to note, for me particularly, is that he's got a keen interest in motorsport and has 2 national championship titles. So maybe we could ask Ian about that a little bit later on. So certainly used to living life in the fast lane. Very much looking forward to hearing from Helen, Michael and Ian shortly. But before I invite them to speak, I thought it might be helpful just to set the scene, to headline some of the things from which the planet perhaps needs saving. The past 12 months, I guess, dealing with the impact of the global pandemic has perhaps given us all the cause to reflect on our own lives and the impact that the planet has on us, and indeed we on it. And whilst bad enough, COVID-19 is not the only threat we face to life as we know it on this planet, nor will it be the last pandemic that we experience. I'm sure we'd agree that we're all facing a number of existential threats to life on Earth. Most of these, I think, relate to the natural world, to our life support systems. And they include things like habitat destruction, loss of biodiversity, degradation of our oceans, climate change. And as Martin was saying, the clock is ticking on all of these. And this is definitely the decade where we need to make a difference. So it's absolutely critical that we need combined and coordinated use of our collective ingenuity to share the knowledge that we have to make the right decisions and find lasting solutions. I think information technology is absolutely fundamental, a fundamental enabler to making those right decisions. 1 million of the 8 million species on the planet face the risk of extinction due to the change of use of land and sea, due to pollution, climate change, or overexploitation of resources. And at least 40% of the world's economy and 80% of the needs of the poor are derived from biological resources. Having greater biodiversity provides greater opportunity for medical discoveries, economic development, and adaptive responses to new challenges such as climate change. And IT plays a hugely important role in protecting biodiversity, for example, to help identify and locate individual animals, to follow their movements, assess the status of their habitats remotely. to help prevent habitat loss by connecting existing sophisticated remote sensing with species occurrence data to predict where those species remain, and then using technologies like genetic barcoding, high resolution satellite data, automatic feature recognition, those sorts of technologies to prioritize species at risk. Nearly 30% of the world is forest, and forests play a hugely important role in absorbing about 30% of the carbon emissions, annual carbon emissions per year, and that's about 37 billion tons of carbon dioxide. Forests are also the home to most of the Earth's terrestrial biodiversity, so something like 60,000 different tree species, 80% of the amphibian species, 3/4 of the birds that we have, and about 70% of the world's mammal species. But since 1990, some 429 million hectares of forest has been lost through conversion to other land uses, and nearly 1/5 of the Amazonian rainforest has been destroyed over the past 50 years. The current rate is 10 million hectares per year, and that's, just to get heads around that, that's about 5 times the size of Wales, or over 12 million football pitches. We can now track the status of deforestation through satellite-based monitoring and data collection systems, and increasingly, technologies like radar is being used to overcome the challenge of cloud cover, obscuring illegal clearing operations during the rainy seasons. And the widespread transmission, communication, and public access to this data is absolutely key to using this to affect the change that we need. Oceans cover something like 70% of the planet. Their temperature, their chemistry, their currents, and the life that they support drive the global systems that make the Earth habitable. Our rainwater, our drinking water, our weather, our climate, the coastlines, much of our food, and even the oxygen in the air that we breathe are all ultimately provided and regulated by the sea. Over 3 billion people depend on marine and coastal biodiversity for their livelihood, and yet we dump 8 million tons of plastic into our oceans each year. And on average, each of us eats around 50,000 particles of potentially toxic and carcinogenic microplastics each year. As greenhouse gas emissions increase, oceans are becoming more acidic, and their oxygen levels are decreasing. Warming oceans cause species to migrate away from their traditional habitats, disrupting food chains. And warming oceans also cause sea level rise, threatening atoll countries, low-lying coasts, and river deltas around the world. And yet, we still only understand about 10% of the ocean's makeup. In 2019, the Intergovernmental Panel on Climate Change, or IPCC, put out a special report highlighting the likely impacts of a greater than 1.5 degrees centigrade warming of the planet. These included sea level rise, species lost, a range of impacts on human health and well-being. And the report highlighted that at the current rate, we're likely to reach 1.5 degrees of warming between 2030 and 2052. And it also highlighted the urgency of reducing carbon emissions to limit global warming to below 2 degrees C. And above this is considered potentially catastrophic. 196 countries agreed to this reduction through the signing of the Paris Agreement in 2015, and recognized that to achieve this, we need to become carbon neutral by 2050. And this, as Martin was saying, this became legally binding in the UK in 2019. But achieving this really ambitious target is going to require a range of innovative technical solutions, as well as shifts in behavior underpinned by robust data, enabling better decision making. And the application of IT is going to play a massive role in this. A key part in cutting carbon and limiting global warming to 1.5 degrees centigrade will be how we obtain and how we use energy, cutting our dependence on fossil fueled energy generation and becoming more energy efficient, and then finding ways to feed and meet the needs of a growing population using less energy intensive methods. All the issues I've highlighted are going to require the application of IT in a range of different ways. Essentially, IT is the enabler for a more sustainable future, allowing data to be shared widely and turned into the information that we need to help make better sustainable decisions and to find more sustainable solutions. In 2002, the US government, for example, agreed to share all of its satellite data on illegal logging activities, which a massive change in their philosophy in terms of making this all open source. And then just to bring us up to date, as another example, the modelling of the likely spread of COVID-19 and the effective measures to combat the virus owes much to the work of Imperial College's COVID-19 response team. And since the emergence of COVID-19 in December 2019, that team has adopted a policy of immediately sharing the code, the data, the tools, the research findings on the developing pandemic. And the result is a much more coherent and joined up response to tackling the pandemic, including the development and the distribution of effective vaccines. And let's all hope that the end is somewhere near in sight. And the recent landing of the Mars rover is an amazing achievement, requiring the combination of so many skills and technologies, and the whole mission is massively dependent upon IT. And it may be that by finding out more about the potential signs of life on that red planet, we may gain a better understanding of how we can live more sustainably on this green and blue one. And to echo President Joe Biden's words, with the power of science, perseverance, and ingenuity, nothing is beyond the realm of possibility. So, having done a little to set the scene, maybe I could now invite each of our guests our guest speakers, Helen, Michael, and Ian, just to share their thoughts and their insights, and then open up for a wider discussion, which, as I said, Amanda's very kindly going to facilitate afterwards. So, perhaps if I could hand over to Helen to kick us off.
Over here. So as Jim said, thank you very much for the introduction. I'm Helen Brindley and I work at Imperial College in London. As Jim said, we've just recently established an Earth observation network there across the college, so I'm representing them today as well. And I also have a little role within the National Centre for Earth Observation that's funded by the Natural Environment Research Council. So with apologies if this is teaching some of you how to suck eggs, I thought it would be a good idea, first of all, to sort of define what Earth observation is, at least according to the group on Earth observation, so you think they might know. So basically, it's as it's written here. So we're trying to use observations to gather information about Earth's physical, chemical, and biological systems. So it spans a variety of different natural sciences, and we use monitoring, but also actually using the information that we gather from the monitoring to assess the status of the climate and the Earth system at the moment, and also how it's changing in both the natural environment, but also in terms of the man-made environment too. So it's not just restricted to looking at natural effects or natural changes. So I thought I'd start off just with a very slightly old slide, but I think quite insightful. So when we talk about Earth observation, we aren't just thinking about satellites, although they play a major role, and that can sometimes be a little trap that people fall into. So this is looking at tools that we've had available to observe the Earth from the late 1900s, and obviously we were looking at the Earth before this, but this gives a good example of what sort of things we use. And we went from very subjective observations where people will basically go outside and look up at the sky to see how much cloud cover there was, to getting more and more, I guess, IT focused. So being able to do things more quantitatively and more repeat with more ability to repeat the observations objectively. The big explosion in Earth observation really happened with the International Geophysical Year, which took place in 1958. And when there was suddenly a great interest in trying to do better at observing the Earth and its climate. And obviously there was also the more recent launch of satellites, and particularly the operational satellite system from about 1979 onwards. And my personal work is very much focused on satellite remote sensing, but I didn't want to miss out the fact that there are these other tools as well, and we should also be considering those when we're thinking about Earth observation as a whole. And these are just three really nice recent examples. So in the top, what you're seeing is someone launching an Argo float off the side of a ship, and these are brilliant inventions that have revolutionized our ability to sound the ocean surface, and given us much greater coverage in combination with GPS satellites. The middle plot is a beautiful image of a forest that's taken from LiDAR, a ground-based LiDAR, and you can basically now sound the forest structure and really see how much biomass you've actually got present in the forest. And then the bottom image is actually a colleague from NCO who went over to Indonesia when there was a very big El Nino a few years ago, and the air quality dropped to something horrific. And you couldn't breathe, which is why he's got his oxygen mask on there while he's taking the measurements of the atmosphere with a ground-based sensor. So these are the kind of things we have available to us. And if we have a look now, just focusing on the satellite side, this is the sort of explosion that we've had in Earth observation capability from satellite over the last few years. So this is going back, this is just looking at satellites from the European Space Agency. So it's not even considering the global picture. It's just one agency. But you can see here, we're looking at the numbers of satellites increasing over time from around the early 2000s right through to what's going to happen as we move into the 2030s. And basically ESA tend to define their satellites according to whether they're using for fundamental science, those would be the science satellites, whether they're used primarily for operational meteorology, so those would be the meteorological missions. And then they've got this new branch, which is the Copernicus Sentinels, which I guess some of you may have heard about, which is basically this new effort to really provide the most comprehensive set of observations of our Earth system and how it's evolving over time from space. And it's a tremendous effort, and there's been a lot of UK involvement in designing some of the instruments that are going to fly on some of these sensors. And there's a huge variety of different variables or different parameters that are being sensed by each of these instruments. They don't just do one thing. Many of them do many things together. I also wanted to not just focus on research satellites, but also look at what's happening in the commercial sector. So this is not my area, but I think it's really interesting. So this is a plot which is showing just the number of commercial visible imaging satellite launches. So this is just one type of satellite. It's looking in the optical waveband and trying to image the surface. So a lot of these are used for things like looking at vegetation, cover. Some of them might be looking at land use change, that kind of thing. And you can see from the first launch of Landsat-1, which was amazing at the time in 1972, there's been an absolute explosion in the last 4 years of this number of these sensors. And I've got some figures that I wrote down. So in 2020, there are 815 Earth observation or Earth science focused satellites. And this was a rise from about 192 in 2014. So you can just see how much of an explosion there's been. Most of those have been dominated by CubeSats, which were obviously linked to Planet Earth and Spire, large launches, but the growth of those is actually slowing down now. And the vast majority of these sensors are for optical imaging. So that's what you're seeing in this plot here. And for the UK in particular, there's obviously interest in this, because when we look at what EO contributes to the UK GDP, so the gross domestic product, from in the last 5 or 6 years, there's actually been a doubling, and it's now up to around £625 million per annum and growing. So this is definitely a growth industry. So just some of the impacts, and I'll be very quick. I mean, Jim actually mentioned many more, and I could spend about 2 hours going through all of them. So that would be far too long for this audience. But one of them obviously is on weather forecasting. So what satellites bring is global coverage, and also the timeliness to get the observations that they're making to the forecasting centers within the time window that they need to be able to use in their forecasting system. And that's normally within, I mean, the quicker you can get there, the better. But it's normally within 15 minutes would be optimal. And you can see here in this plot is it's a plot of how much each measurement has made a contribution to the forecast error reduction. So AMSU-A at the top there is a microwave sounder. Microwave sounders are particularly useful because they can see through cloud. So you can see in both cloudy and non-cloudy conditions. And they made a huge impact on the error in the forecast. And this is data from the European Centre for Medium Range Weather Forecasting. And practically all of the things that you can see there, except for the air rep and the surface synoptic sites and some of the winds, are from satellite instrumentation. Okay, so it's all Earth observation, but it's dominated, the reduction is dominated by satellites. And the little plot I've just put on the right-hand side there is just to show how it works. So it's by a method called data assimilation. So the way that we get our forecasts today is to merge, very intelligently merge, the observations with a model prediction. So you make a forecast, the observations get to the modeling center within a certain time window, as I mentioned, and you basically use a technique called 4D data assimilation to correct your forecast according to the observations and the errors associated with those observations, and then you get a better forecast. And this has also been used very successfully in something called reanalysis, where we go back and look back in time and gradually try to incorporate all our old data that maybe wasn't used at the time because it didn't get to the forecasting systems in time, to create the best estimate of how our climate has evolved over time, going right back to the beginning of the 20th century. So this is quite a remarkable achievement, and reanalysis has really revolutionized some of the work that's done in weather and climate. So if we just keep going, not only are we using it obviously in weather, but we're also using it in terms of producing climate records, as Jim said. And maybe the big push here is to try to produce what we call essential climate variables. So this is an initiative that's been led by the Global Climate Observing System, GCOS, and they've looked to see what can we actually develop, what variables can we get over a long time period with sufficient accuracy that they are going to better characterize how our climate is now, how it's changed, and how it's going to change in the future. So there's three criteria that they put on a variable that allows it to be defined as an essential climate variable. It has to be relevant, obviously, has to be feasible, so we have to know that we can observe it using a scientifically understood method. And it also has to be cost effective, which is an interesting one. So can we actually generate an archived information with an affordable cost? And this is both in feasibility and in cost effectiveness is where perhaps IT could play a role, actually, in terms of defining what kind of technique we can use and making it more cost effective to actually make that measurement. And currently there are about more than 50 essential climate variables which span three domains: the atmosphere, the land and the ocean. And you can think of typical ones like the precipitation, surface temperature would be an obvious one, but also things like above ground biomass, land cover, probing right down into ocean salinity and things like this, and soil moisture. And even now there's two new ones that I just noticed the other day, which are focused particularly on what we're doing. So they're called Anthropocene variables, and these are things like water use and greenhouse gas fluxes that are coming from human activity, and we now believe that we can do those accurately enough to actually create these records, which is a real step forward. I'm not going to talk about this too much, but I put this in because this is my work. But basically, we're also creating, enabling fundamental advances in climate science by making new Earth observation measurements. So these are a couple of missions that are going to come about. The top one will definitely come about. The second one is still under study, where we're actually trying to make those measurements that actually underpin our fundamental climate science. So the top one in particular is trying to look at the outgoing long wave radiation from the Earth. So this is the energy that the Earth emits. It's very fundamental for working out what the Earth's greenhouse effect actually is. And it might surprise you to know that we have never actually measured the spectrum of the outgoing Earth's energy from space for the Earth at wavelengths longer than around 15 microns. And this contributes about 50% of the greenhouse effect. So it's a fundamental measurement that should be very interesting, but it will also give us a lot of information about other variables like water vapor, cloud, and also surface properties. I'm going to flick this one on because I'm conscious I don't want to use up everybody's time. But I wanted to show what we can do in terms of monitoring hazards. So this is a really nice animation of fires burning. It's a measurement called daily fire radiative power. So it's basically giving you an indication of the intensity of fires around the globe. It's something that's produced by the European Centre for Medium Range Weather Forecasting in combination with measurements that are coming from the Copernicus Sentinels. And it really gives you an indication of the power of the sort of things that you can do and really direct where to go in terms of disaster management, disaster mapping, that kind of thing. There are many more examples of this, but this was just one I thought looked rather pretty. And then if we can get this to move on. Obviously, we might also be familiar with this too. So I'm pretty sure that everyone might have seen this in the news over the last year. So this is not only in terms of what we're doing to climate, but also what we can use or what we can learn from climate measurements or Earth observation measurements about what we are doing to the system. So this is the change in air quality from before lockdown to after lockdown. And what you're seeing is a cleaning of the atmosphere. And we can see that from space quite clearly. And again, these are measurements of nitrogen dioxide, which is a measure measures air quality and is particularly affected by things like fossil fuel combustion and diesel emissions. And you can see the very, very strong drops in those values. It's an interesting, someone later on asked me about carbon dioxide in this as well, because it's an interesting question in the context of trying to meet Paris agreements. So I just wanted to finish off by saying some of the outstanding challenges that we have, at least in my perspective. I mean, this is all from my perspective, and I'm sure that there are other scientists that would say other things too. But I think the key thing for me is thinking about how we're going to archive all of this Earth observation data that we're actually producing. So Copernicus is producing 12 terabytes per day, which is quite a lot. But if we look at how ECMWF, the weather forecasting systems are using that along with their own modeling, in 2017, so this is out of date, their data archive was growing by 233 terabytes per day. And the size of their archive that they have in their systems has doubled from 125 petabytes in 2015 to 220 petabytes in 2017. So it's almost a doubling in 2 years, and I'm sure it's grown much further than that since then. So how are we going to archive it? How can we keep the required metadata that we also need to be able to interpret those data? Can we ensure that people who need the data get timely access in the right format and in a way that they can understand for the use that they need? So it's fine if I go along and say, okay, I want that data. I can get it at the very raw level and I understand what it means, but it's not going to mean anything for someone who actually potentially wants to use the data in a different way. We've got a lot of data coming online now, so how do we properly merge it together? How do we make those data streams merge together to create something that we can use in a complementary way? And an example of that is in the image in the bottom left corner there, which is a sort of idea of using data cubes. But I'm sure there are more exciting ways that we can merge the data too. And there's a lot of interest in developing your analysis tool. I mean, they're buzzwords at the moment. If you put this in any of your proposals at the moment, you stand a greater chance of getting funding, which is a little bit sad. But there's no doubt that people are looking to use advanced techniques to analyze these data, neural networks, deep learning, machine learning, artificial intelligence, all those kind of things. There's also the question of possibly even working out how you could use developments in computing, so quantum computing, to analyze these data. And then we want to also try and think about how we can identify gaps in our current observing system. So once we know there's a gap, we want to identify and measure a particular variable. How can we develop the technology to actually address those gaps and fill that gap?
Helen, thank you. Thank you so much. I think it's absolutely fascinating. I'm sure that's stimulated lots of questions. What I would suggest, as we said, is perhaps we could, unless anybody's got any really burning question right now, we could perhaps leave those to the Q&A. But thank you so much. I think that's really fascinating area of science and the application of IT. So thank you. May I now ask Michael if he could lead us through his thoughts as well? So that'd be great.
Yes, thank you, Jim. Well, firstly, it's a real delight to be back at another WCIT event, and I'm delighted that the company is taking climate change and the environment so seriously. We know the cruciality of the theme, and thank you, Jim, for your introduction. What I'd like to just touch on is the question of how IT can save the planet. And I think my overall theme is basically that IT is crucial, but there's no killer application. And people who are seeking that, I think, are wasting their time. But what it is definitely about is IT helping billions of people to make trillions of better economic decisions. And the time to start really is now. I presented, I believe, a month ago, sort of a point about the city, and what is often forgotten is that the city's been involved in the climate change debate for some time. And I have personal experience of that. And the story that I shared was that back in 1984, I had a debate on climate change, and we ended that debate with, does society want to pay? That's the biggest thing. And I believe that we're moving into a position where some 37 years later, we're beginning to get there. But even there, people are still not wanting to confront the real numbers. And I'll just give you a little challenge here. The back of the envelope calculation, the average Briton emits 8 tons, just over 8 tons actually, of carbon a year. The current price to avoid emissions is over 30 euros a ton. Multiply 8 by 30, you get 240 euros. And that's basically 1,000 euros a British family per annum. And those are really the costs that we're facing. We're beginning to face up to it, but those are the costs that we're facing. So this to me is the big opportunity for IT. Now, my firm happens to run the Global Green Finance Index, and across the board, things are broadening out. When we began the index a few years back, the only things people that cared about were green bonds and ESG ratings. And now, as you can see in this diagram, it's spreading out a little bit more into areas like SRI investment, natural capital valuation, disinvestment from fossil fuels, energy funds. So we're beginning to see the areas starting to show a much richer, and I use the phrase with some trepidation, ecosystem about what we mean by finance. Now, the other thing about this is people frequently say, I don't know how we're going to get there. Well, there's certainly going to be many unexpected bumps and turns on the road ahead, but we do have roadmaps. Stephen Pokala and Robert Sokolow, we're looking at climate change mitigation scenarios back some 17 years ago with their WEDGE program. We have a number of people laying out various routes to decarbonization, but all of these come with large economic bills. And I think one of the big mistakes that's made is to assume that all that money has to be piled up in one pile and used. In reality, what we're going to be seeing is, as I said earlier, trillions of economic decisions. And those economic decisions are going to be coming at us from a number of ways. And I would highlight in principal ways, a lot of the focus of the NGOs has been on top-down pressure on capital allocation. That's the ESG approach that WCIT had a debate about last week. And the presumption there is that markets are failing and we need taxonomies and disclosure will drive everything. As we agreed last month, this is an approach, and it's an approach that's useful. But probably more important is the bottom-up approach, people making billions of economic decisions, using markets, pricing, buying products that are cheaper, because they have actually handled their carbon emissions, to take that, or have handled a reduction in their wastage or water usage. So in this case, we can see that the two methods will be working together. So I'm not claiming markets are everything, but if we can internalize those billions of decisions are easy to handle. They're equally easy to handle if they're incorporated in taxation costs, but some of the regulatory and the ESG shareholder values have got a limited ability to help us. And we're beginning to see people moving towards how that would work. Now, I was asked to make some comments as well about the fourth industrial revolution. For those of you who are not familiar, the first is the iron and steel of mechanization that began near Iron Bridge Gorge up in Shropshire, the sort of home of the Industrial Revolution. The second was energy and transport and mass production. The third was the early stages of computing that many of us participated in, computing and connectivity, 1976 in the internet, 1972 in the internet, etc. But this fourth one is about the sort of pervasive cyber capabilities of physically integrated infusion, AI, big data, the things that people trot out at every conference. Have you thought about AI, big data, distributed ledgers, blah, blah, blah. I think the big jump, though, between the third and the fourth does have some validity. The first is that there were two big mistakes made in the third. One is we really never paid attention to security. Passwords and payments were never really put together properly. Passwords were there really on a multi-user system that another programmer didn't overwrite my stuff. I wasn't there to guard my credit cards and my bank account. The second area is we focused on communications, but not on records. And Helen made a really good point about the scale of the data. Fine, we're recording it, but how do we access? What's the metadata there? So we're moving a lot more to sort of internets of record, where we can record things using distributed ledgers that allow us to go back with some ability to realize what's going on and that it's authoritative, it hasn't been changed. But we do equally have a huge storage problem. And into all of this, as many of us in this sector will know, fintech is deeper than you think. Fintech actually matters here. if all of these transactions have got economic costs, which they do, fintech could be part of the solution as well. So to some degree, the fourth industrial revolution is just a recognition of the obvious. With ubiquitous computing and connectivity and lots of data, lots of processing power, expect things to be innovative and to trot out AI and big data and blockchain at every opportunity. It's not really about IT. The innovation is now about the challenges and the economics. So we've seen the power of IT to some degree. During these various lockdowns, global emissions have dropped by just over 6%, largely due to IT. We've been able to video conference and keep ourselves going. Another example here is Google's electricity usage, which rises every year for obvious reasons. But DeepMind, the British machine learning company which they purchased, reduced Google's data center cooling bill by about 40%, well, at least on a good day. So IT is definitely helping. Another point is that, interestingly, this slide shows you that over time, data center energy use has been nearly flat, believe it or not, for 10 years. We use in data centers about as much as we used in 2010. And at the same time, the workloads, the amount of processing units has gone up quite substantially, and the internet traffic has gone up by a factor of 12. So you might say we're doing a very good job. On the other hand, IT is part of the problem. And this slide gives you some idea of the scale of it. Down on the bottom left, IT is running at about 11% of total global energy usage. When you move beyond the data centers and take into account consumer devices, mobile networks, Wi-Fi networks, wired networks, and consumer devices. So we have a big task closer to home in terms of what we're going to do about IT and the planet. In a sense, we're using a devil to catch a devil. So we need to make sure we get returns from our own use of IT. And some of the breathless claims out there about blockchain in particular, at least Bitcoin and consensus-based blockchains, would actually make IT an enormous problem. It is true, blockchain is currently running, and this is from today, by the way, a carbon footprint the size of New Zealand. The electrical energy consumption is the size of Chile. And you can see that you're looking at, just to make a single transaction on blockchain, you're using the same amount of energy as a US household would use in 23 days. I put up here a little thing I just wanted to check out this morning, which is interestingly, I thought, what's the market cap of Google compared with Bitcoin in terms of energy consumption? And you can see here that to support a slightly larger market cap than Bitcoin, Google uses 12.4 terawatt hours per year, and Bitcoin uses 78. So this is not the way to save the planet. So could we please avoid Bitcoin and blockchain and cryptocurrency transactions as part of our discussion? But everything starts with a roadmap. And given that my initial claim to fame technically was the original digital maps of the world in the 70s and 80s, I'm delighted to, with anything that starts with a roadmap and Earth observation. And in fact, we're working with a company here on the top right, Earth Knowledge, which is using the maps of assets around the world and correlating those with the risk that's associated with various types of environmental exposures of temperature, flooding, land stress. It's a really biodiversity loss. It's a really interesting approach there. But what might surprise you is that IT is able to handle wider problems. And amongst the top 10 solutions to climate change from another rather credible study, their roadmap has things in here like refrigerant management, which sounds boring, but is in their opinion, the most important thing to avoid climate change. Or if you look further down there, you'll see educating girls at number 6. So there's a much wider area where IT can make a difference. And so if you're building automated education systems of various forms, you might find that you're doing the world a heck of a lot of good, and more than some of the perhaps trendier ways of tackling the planet. Well, just to bring my comments to a close, the first thing is that we've got to understand that innovation really comes from two areas, and strangely and rather crudely, war and bubbles. And that's because innovation has high degrees of wastage. If we knew where we were going, we would go there. The point is we don't know where we're going. So these billions of economic decisions won't always be right. And I'm expecting the investment community, which is teeing up for this, is already beginning to complain about a green bubble. And that's not necessarily a bad thing. So what's IT ever done for the planet? Well, we could fill in a chart like this. This is a chart I constructed some 35 years ago, believe it or not, to look at where you could contrast the benefits that you were seeking on the left with things like time, place, function, or consumption. And we could go through and populate that, and you begin to see that IT is ubiquitous, is everywhere. So maybe those fourth generation people have got a point. So to close, saving the planet. Well, if you're going to do it one bit at a time, probably the biggest thing is, if you're politically minded, focus on the fact that government policy risk is the distinguishing factor in green. If we had seen some 36 years ago, 37 years ago, more determination from governments to make it cost, we'd be a lot further along the road. And so we have high hopes at COP26 that screw of policy is going to tighten. The second thing is, I believe markets need to be made to work, and they are being made to work, but just too slowly. And so whilst we can focus on top down, we really need to get bottom up working rapidly. There are big opportunities for IT everywhere, probably in a lot of these markets: carbon, energy storage, smart transport, smart energy markets, as well as land use management, which requires heavy earth observation, and smart cities, urban planning and design. So I would suggest that what we're really looking at is how IT helps everybody on the planet make better decisions. And that could be our biggest contribution to saving the world. Thank you.
Michael, thank you so much for that. As ever, a very thorough and really interesting exposition there. You talked about energy storage. You talked about smart transport. I think that's a good segue perhaps into Ian's slot. So if I may hand over to Ian to take us through his insights.
Okay, lovely to be here. So thanks again for inviting me. So what we have is, starting off with a picture here of my co-founder Jan, so in our battery lab at Imperial, so probably very close to where Helen's doing her research. And we'll take you through initially a little bit of the journey since we came out of the college, what we do in the battery space, and then I think link that up to how it fits into both IT and saving the planet. So my name is Ian Campbell to begin with. I'm the CEO of this company, Breathe Battery Technologies, and we spun it out of Imperial College London's Department of Mechanical Engineering back in 2018, 2019. The reason it came out of that department is that there we have the Electrochemical Science and Engineering Group, which is led by one of our other co-founders, Dr. Greg Offer. So that group focuses on supercapacitor research and battery research, primarily batteries, a couple of different chemistries. And as part of a wider group at the university that focuses also on a bunch of different energy storage and power generation topics and methods, including fuel cells. So why did we do this, and sort of what's the background to it? We were doing a lot of consulting work. I suppose at the time I was at the university, which was 2015 to 2019. We were consulting sectors from finance on sort of investment decisions related to electrification of transport, to companies who were doing some robotics that were relying on batteries, and we saw over and over again that companies were having some technical challenges with electrification of products, and there was really a lot that could be improved. I think in that area, and we saw that starting a company would be a very scalable solution to tackling those problems. We were very lucky at the time to get some support from the Faraday Institution, which you see listed here, and the logo on the right hand side here. And to date, they've been one of our biggest supporters. And just some context, that the Faraday Institution is the research and academic supporting arm of the UK government's Faraday Battery Challenge, which is the government's big push for battery technology development now in the UK over the last number of years and going forward through this decade. And I think mentioning that decade is coming back to a point that Martin said at the beginning of this call today, and I said decade of delivery. And I think the context for us starting the company in the 2018-2019 period is we're looking at this decade between 2020 and 2030 until we have a ban on internal combustion engine vehicles, forcing both regulatory policies and the climate requirements are forcing so much change in the vehicle industry. So what do we actually do as a company, and how does it fit with IT? Well, we make software, or more specifically firmware, for battery management systems. So I think very much in contrast to when I was a kid growing up with batteries like nickel metal hydride, so NIVs, and maybe NiCads, nickel cadmium batteries, which were quite passively managed batteries. Today, the predominant chemistry, I think we'll all be aware, is lithium-ion chemistry of various different forms in many different industries. But it's very different to those older batteries in that it needs a very active level of management. And that's even more true the more performance we want out of that chemistry, or the more safety we want out of that chemistry. And it becomes more true again when you get to very high value battery packs, like those that we see in energy storage systems connected to the grid, or like battery packs that are many thousands of pounds in electric vehicles. And on that point, that is the market focus that we have with the company. And this is of course the link to the climate, and to the name of the company, and to really everything that drove us to do this. So we'll get into that. So in terms of founding team, I mentioned already the first slide, Dr. Yan Zhao is a co-founder of ours. So he was also carrying out a PhD at the university at the same time as me. Dr. Greg Offer, our third co-founder still today, is leading that research group at Imperial College London. Together, we have over 22 years of battery engineering experience in this domain. And I think you'll understand this was a little bit of background in terms of making a company out of this technical basis. Is we need some advice, especially on the commercial and technical side. We have that in part through this advisory board that you can see in front of us. And one of the most relevant ones, or most interesting for the audience here today, might be Professor Andy Hopper, who's the head of Cambridge University's Computer Science Laboratory. Andy was also previously he was previously co-founder of Acorn Computers that spun out the division that became ARM. So he himself has quite a legacy in this sector. Before we get into, I think, how we're actually achieving it, a little bit more in the context, what we are trying to do and why we started the company and why it's called Breathe is we're fundamentally trying to tackle two problems, and the purpose of the organization. One is tackling air pollution. We're based in London. I think we experience air pollution here like every city around the world. And I thought Helen's map of the nitrogen dioxide concentrations, and especially the change during lockdown and over the last year, has been, it's very interesting to see, but also very, very good example, and very clear example, I think, for the world and relevant to what we're doing with the company. The other thing that we try to tackle is climate change as a whole. And the way we try to approach this is I think, very nicely summarized in a graph that I've kindly borrowed here from Bloomberg's New Energy Finance division, from an annual report they have, which is very, very good, called the Electric Vehicle Outlook 2020. And critically, what we're looking at here is a green curve, which is showing the trajectory of electric vehicle stock increase as a fraction of the total annual sales of vehicles by powertrain. And at the same time, over the coming sort of 3 decades here to 2040, or 2 decades to 2040, sorry, the internal combustion engine vehicle stock reducing and sales of that reducing. What we are trying to do as a company is drive this curve up higher and drive it up higher faster as well. And we believe that we can fundamentally do that by improving the performance of batteries on a couple of different metrics, and by enhancing the safety of those batteries, and additionally by reducing the cost and time it takes to get vehicles with battery electric powertrains to market. And yeah, I think so. This is I think the quite clear climate link. Before we get into maybe a little bit of the technical thing that we do as a company and how that's IT related, some additional context I think for the battery space is good. So there's a whole bunch of battery companies out there today, and I think I see it, and we all will see it, especially in the popular media and in academia as well, and so many technical publications today. It's I think when I was doing the PhD, people were correctly summarizing the state of battery publications as trying to drink from a fire hose these days, which is good. But all of these organizations, whether they're academic or industrial or another, are pursuing improvements to battery safety and performance by really 4 possible methods. And we can start with what we maybe most often see in the popular media, the post lithium-ion chemistries. So maybe what comes next, the big battery breakthrough, and maybe something called lithium sulfur, or maybe solid state batteries, maybe lithium air, some replacement for lithium-ion. This is very high risk stuff, but with potentially very high reward and very game-changing levels of performance and safety. A second approach to improving battery performance and safety is to change the materials in the existing chemistry. So maybe to tune the mixture of nickel, manganese, of cobalt, of graphite, and various different additives in electrodes or in electrolytes in the system, in the lithium-ion system that's predominant today and has been for the last 30 years. There are two more then that I'd say are probably less talked about, at least in the popular media. One is to try and improve the battery hardware or the hardware systems. So we might be talking about here how you configure cells or how you configure individual batteries in a battery pack for optimal usage of that pack's volume or optimal, let's say, mass minimization. We might be talking about thermal management system tuning and optimization as well to try and enhance the performance and increase the safety as well. And then there's a fourth area, and the fourth area is where we've very intentionally positioned the company that we spun out of the college, and that's using software or taking a very IT focused in this context approach to enhancing the safety and the performance. And this is the stepping stone to me explaining, I think, how we do that. And it links back directly to the fact that today's lithium-ion batteries and every battery going forward in the future needs a very active level of management. We can do that in very many ways. We have a lot of levers to pull. And for example, what we do today as a company, or we set out when we built our first battery modeling platform and our first product, we decided to pull the charging lever because it's an option that allows us to have a very large degree of control over the level of safety of the battery and performance. So we today produce firmware specifically for microcontrollers in both consumer electronics devices, so your smartphone, your laptop, but primarily for the battery management systems in electric vehicles. So we talk here about now the sort of circuit board that sits alongside the battery pack and is responsible for extracting the full performance that's available from the materials in that pack and for ensuring the safety of that battery pack across its lifetime. That PCB, that BMS, it's very analogous in the electric vehicle world to maybe something that's people are more familiar with, like the engine control unit, the ECU in the internal combustion engine vehicles. So I'll show you now, I think, a nice example of what we do and the approach we take and how it's, I suppose, quite IT focused. So there are really only three things that you can measure with any battery pack. So whether it's your phone or whether it's your expensive car or an even more expensive grid-connected battery, you can only really measure the temperature. You can measure the voltage, and you can measure the current going in and out of it. Excuse me. And if you want to make decisions based upon those measurements, you really don't have a lot of information to make those decisions on. So that can be quite a challenging situation. And decision making directly drives the level of degradation or the aging rate of those batteries. And aging is everything because it directly affects total cost of ownership. Excuse me, of those batteries, and it also directly affects the return on investments and the cost of the system as well. So what we try to do as a company fundamentally is pursue a process called state estimation, where we use mathematical models that we implement in software that run on these microcontrollers in real time, or in the, let's say, cloud versus edge paradigm, on the edge or on embedded systems. And when we use those physics-informed or physics-based models of batteries to infer what's happening internally, electrochemically, thermally, and sometimes mechanically, and then to make in real time what we believe are very well-informed decisions about how we should control the battery. And I show here an example on the slide of a standard charging process today, something called CCCV, which is constant current charging, and very typically how we charge, for example, our smartphones today. And what we're really focusing on here is the potential of one electrode in one degradation example, where as the battery evolves from the first day we have that device or the first day we have that battery until its end of life, from black to light, these profiles of these electrical potentials evolve, and they spend a lot of time beneath this red line. And that red line is indicating here the onset of quite aggressive degradation of that battery. And these are not measurable quantities normally, and this is the kind of result that we achieve with state estimation approaches. And what we do is then control the batteries in a different way and quite actively on the edge during their usage, both during sort of on a range of different timescales, so on a second-by-second basis, but also month by month and year by year, to keep the batteries operating in regions that are healthy and don't accelerate the rate of degradation of those batteries. And the result you can achieve is then you see for the lifetime of this cell. So from black to light colored curves, we maintain them above this red threshold, let's say the dangerous region that we want to avoid. That directly enhances the safety, and also, you'll see it here, directly improves the performance. This is a reasonably straightforward graph of cycles, so the number of times we've charged and discharged a battery, moving from 0 to the end of life here on the right-hand side, and then the capacity or the health of that battery on the vertical axis. And in that example there, what we looked on the previous slide, that the standard scenario is driving down this gray, quite steeply sloping curve, where we're losing capacity, and that means that you basically have less vehicle range, or you have less smartphone or laptop runtime, and then you reach a state where, let's say, the battery can be deemed unsafe or no longer having the capacity to meet its purpose earlier than if you control it intelligently using these mathematical models. This is the value addition to the markets, and it's also the way that we can prevent unsafe behavior, especially later in life, and the kind of thermal runaway scenarios that we might see with various different publicity levels in the media, like these kind of Samsung Galaxy Note failures of a couple of years back. So that's the super brief intro. That's the end of the slide deck. I didn't want to get too heavy on the presentation. I think I'd like to leave some time for Q&A, because I think it's a very broad area, and I think I'd like to leave it to you to drive maybe where you'd like a bit more information. So thanks very much for listening.
Ian, thank you so much, and that really, again, really fascinating and very encouraging as well, particularly for those people that are concerned about, have range anxiety with their batteries. But I think it's a broader issue than that. So thank you also to Michael and to Helen. I'm now going to hand over to my colleague Amanda, who facilitates our short Q&A opportunity.
Thank you, Jim, and yes, huge thank you to our speakers, and three very different perspectives on IT's role in saving the planet, and all equally vital and fascinating. Yep, Leo.
Starting with the last presentation, and with a personal interest because of old technology, because in my spare time I'm restoring the 1950s electric coal lorry driven by batteries. But the question is, the efficiency of your IT working on controlling the batteries and the life of the batteries is very interesting, very important. But what about the energy that goes into the batteries in the first place? Because, batteries have to be fed by power stations. And is there any work you're doing on making these batteries more efficient from the point of view of the amount of energy that comes in the first place? Or is it simply energy in, energy out?
Ian.
Yeah, I just unmuting, so let's forget that. Yeah, is a very valid question. So I suppose if I tackle it in two different ways, very briefly. On the one hand, if we talk about strictly in technical terms, the energy efficiency of lithium-ion systems, so what we would buy on our phones and what is going in these electric cars, is remarkably high. So the amount of energy that we put into the battery versus the amount that we get out is less than 1. There's a small amount of inefficiency, but it is in the region of 95% plus, very, very typically, depending on the materials. It is basically a super energy efficient process. And then I think you touched on in your question, if I understand correctly, in terms of the energy or the cleanliness of the energy that goes into the battery packs as well, especially as we move to electrified transport. I think it's very much a two-pronged problem. We very much sit on the vehicle side, on the application side, and I think with a very clear recognition that the transport systems of the planet need to be electrified. And we talk about electric vehicles, we don't just mean cars, we mean also aircraft and boats and the marine sector, everything in the future. The grid also needs to be cleaned to provide clean electricity to them. I think they're very separate problems, and I think the very a somewhat painfully common criticism of electric vehicles when there's a dirty power grid isn't justified, because there are two separate problems. Both need to be solved, and not tackling electrification of transport because of a dirty grid isn't a solution at all. Yeah.
Ian, could I ask you, would your battery technology replicate across to the grid? Because that is one of the problems, isn't it? If we have a green energy supply with solar or wind, for example, it's storage is one of the issues that we're struggling with, isn't it? Storage of energy from the grid. Is it something that your enhanced battery technology could just be?
I could almost answer for you and say nobody's sold that yet. We're waiting for it.
Yeah. It is indeed, Amanda. So we're in, I think, strategically quite a good position as a company, because what we develop technically is very market agnostic. So we target electric vehicles for various reasons. But in the future, the plan is to tackle quite a range, including the grid. And we have had some active projects on that. We in fact just finished an Innovate UK project on the grid that turned out very well. So I'd say we're actively exploring these today.
Excellent, thank you. Do we have another question? Probably best if you just shout out. Oh, Martin, please.
Yes, I've got a question for Alderman Professor Manelli, really. I think it's fascinating what you were talking about. I work in aviation, which is highly regulated. And one of the things I'm picking up, which is quite interesting, is our policymakers are looking to reward first movers in a lot of these things. And I just wonder if that's something you've been thinking about, and how regulatory policy regulations might sort of reward the first movers in this, that starts to create markets.
Yeah, it's a deep point, Martin, and of course it plays to the role of competition as well. There are quite a few disasters, economic disasters around the planet of policymakers trying to reward first movers. I'll give you a good example is California in the 70s on wind power. And what's tended to happen is that by subsidizing the industries in a quite a mindless way, they've in fact made them complacent, and because they're complacent, they become uncompetitive and they fall apart. And so the history of first mover advantage is an interesting one. We are having very active debates, as you can imagine, on the subject of where innovation and deployment come from. And I might contrast, you've got people like Bill Janeway, who I mentioned there, would contrast, of course, with somebody like Mariana Mazzucato. Personally, I'm probably much more of the Janeway school, principally because quite a few points in Mariana's books are wrong, including her points about how the internet was actually created. She completely ignores the fact that the internet was really created by a firm called Bolt, Beranek and Newman in 1968-69 in Boston. And whatever you read on the literature tends to be written by governments who are like DARPA, government agencies that are trying to claim that they invented it, because nobody's there to fight for Bolt, Beranek and Newman. It was absorbed into another firm 35 years ago. And so there's a lot of strange views of the history of where innovation comes from and how it's deployed. It is clear that where it gets it right, though, is when the infrastructure elements are there. And I keep trying to say to policymakers, it's not that you can't help innovation. It's not that you can't help first movers, but you've got to provide a very broad base. And a current angle here, and I'm sure Ian would certainly have a thought on it, perhaps Hazel, is the current move towards electric vehicles is likely in the United Kingdom because we're rushing towards targets to preclude hydrogen. We just won't have time to develop hydrogen. I'm not saying hydrogen's the most wonderful thing. I'm not saying that electric cars don't have a role, but those types of decisions cut off pathways that you might want to explore. And I could, if we had a longer time, dig out many other examples where people have rushed to get something done and then wound up falling behind.
Thank you.
Yeah, thank you. Any more?
As a consumer, I'm interested to do something, but there are all sorts of barriers. For instance, I live in the middle of London. I live in a house that is a grade 2 listed building, which I'm forbidden to do all sorts of things with. I can't possibly charge my car unless I walk 10 minutes. These are big problems which people don't seem to be talking enough about. The only thing that I am interested in, Helen, is I do lend Imperial College my phone and my iPad every night to do COVID calculations. So although it's not climate change, at least I feel I'm doing something by lending that, as with 100,000 other people. And it tells me how many calculations I do a night. So I mean, I think you know, there are lots of consumers who probably want to do things, but you know, can't do it. So what's the panel's views on that?
Helen, might we start with you?
On that thing particularly, I mean, citizen science is a big growth area, and actually there was a really nice project focused on climate modelling a few years ago, run by Oxford University, which was fantastic and got lots of people involved in doing their own calculations independently at home, just like the COVID one now. I don't know. I always think. I often hear the comment, we can't do anything individually. It has to be done, led by government. We can't make a difference if we don't do things, you know, we're too small. And I don't think that's true. I think everyone can do something, and every little bit that you do is beneficial. So even if you're only thinking, I mean, we've seen this great explosion in people being able to recycle, which wasn't around when I was young. You know, it's much more common now and people know about it. It's still not perfect, but it's getting there. We see the move towards, you know, can you put in energy efficient lighting? Can you do all these little steps? Can you put in, I mean, I know it's difficult with the grade 2. I live in a farmhouse, so I know where you're coming from, but is there any way to make your house more energy efficient in other ways? So I think we can think about it that way and just try to make small steps individually, and that can make a change, and not use the excuse of, you know, it needs government to do things before we can act because we're too small to make a difference.
Helen, I would pick up on the data you showed us too about the CO2 monitoring during the pandemic, which clearly shows that if we journey less, and presumably a lot of that was flight related as well, and if we fly less as individuals, and if we consume less energy and therefore make fewer emissions, we will have a direct impact on the planet. And you've been able to map that and evidence that.
Yeah, I mean, what I showed was actually nitrogen dioxide, but there are studies that have shown that, quite recent studies that have shown that the CO2 emissions from fossil fuels have decreased. Perhaps not as much as you would expect, actually, given the scale of the disruption. Michael talked about it a little bit in terms of carbon emissions. The slight, I mean, and that's great. I think the worrying thing about it is that, you know, this disruption has been quite large. It's been, you know, quite prolonged for some people. And when you look at the scale of how much the drop has been, it's not very big. So it tells us that we need to make major changes to make this work. And if you look at what's happening to the CO2 atmospheric concentrations, they are not changing, they're still growing, even with this emission reduction. So it's nice to see. It's nice to see that it makes a difference. Changing our transport habits in particular does make a massive difference. But it's not enough on its own, and it just speaks to the sort of changes that we do need to make at individual level and at governmental level.
I wonder if Ian and Michael would like to comment in response to the question about Mark's question about small, you know, what difference does an individual make? Michael, perhaps.
Well, I think this is the big lesson I draw from COVID, is an extension of how the point I was trying to make is it's dropped 6.4%. That's the number. So we're not going to get there with small behavior change. It is true that small behavior change matters and we should do it. But I think we've got to look at these bigger issues. In the opposite of Mark, I live in a relatively modern block of flats, but we can't get anything done because to do anything requires 56 lease alterations. It's not a joke, you know, we can't afford it. We can't afford the lawyers to put in some of the gas plants we were looking at years ago and things like that. But I had a question really for Helen, whom I'm afraid I just realized I called Hazel a second ago. Sorry, Helen. Quick question for you, which is related to the IT group. We're seeing a lot of fragmentation around the world on data and data rights and things. And most IT people tend to support open data movements. Do you see a danger there in the Earth observation area? You know, I think we're going from about 1,100 satellites to about 10,000 satellites in the next 10 years. And yet they seem to be compartmentalizing into low Earth orbiting networks, which might go private or walled garden. Suddenly we've got EU stuff, suddenly we've got British stuff. You know, when I was in this in 76, NASA basically gave all the Landsat data away for free. So where's this headed, and could the worshipful company help in some way?
I think it'd be great if they could help. I mean, I personally do not use high resolution satellite data. Mine is super low resolution, but I know that the guys in engineering, for example, and those who are interested in the land surface particularly, really want access to commercial data. And it's a real issue, actually, to get that access. So if we go ever more down this commercial route, I think, yeah, there's a problem because you have to pay for it. And it's expensive. If it could be made free to access, that would be marvelous. I mean, conversely, I will say that ESA are going down the other route. They've always been down that route anyway, but they're very much going now towards not only open data, and we're still in it, even though we've left, well, we haven't left Europe, but we've Brexited. We can still access the data, we can still manage that. But I think they're going very much down the route of not only having open data, but also having open source coding to how you actually produce that data as well, which is a really key aspect of this, because you can go back and actually see how the data has been produced, which is important in my field, at least, for monitoring climate. So there's two competing things going on there, but it's a really important point to raise.
Can I just build on that question? Actually, I was just wondering, is the resolution of infrared satellites good enough that you could monitor houses in a street for the insulation that they've got and things like that? I mean, I was just wondering if there's practical public uses of this data.
Infrared is typically less spatially resolved than visible, but if you had access to the military satellites, I'm pretty sure you could do that.
Perhaps that's
I think technology exists. The technology exists. We don't see it, but you could, you know, the sort of things that we see are the stuff that you look at, sort of night lights, and that kind of thing, and you can drill down now to see sort of individual oil flares and things like that.
Just remains for me to thank on your behalf the speakers, so Michael, Ian and Helen, thank you so much, absolutely fascinating, and thank you all for joining us this evening, and David for organising, and Melissa, I think she might have gone, but thanks to her. But a huge thanks to my colleague Jim, because I got some credit and I deserved absolutely none, because he did all of the work. So a huge thank you to Jim on your behalf, from me and from you, I'm sure. And I think that draws this evening to a close. Formally, David, may I hand over to you?
Amber, yes, thank you very much. And just to echo Leo's comments, and thanks to you all, I think everybody here should just show their appreciation in the traditional manner. I think, thank you very much indeed.